It's time for more calculus. Whoop whoop. Let's do this thing. Daily lessons 128 and 129. Let's go. Okay. Oh, my chair is so squeaky. Consider these points the value of a differentiable function f of x. That's nice that we know it's differentiable because we know that this is a nice smooth curve. This is my function f of x. Great. In the table below, plot the points. So when I'm plotting, this is going to be f of x. And I did this already. Take a moment to do this now. So plot the points. Okay, so after I plot this, it says in calculus, the derivative has many interpretations. One of the most important is that the derivative represents the rate of change of the function. Yes, rate of change. The derivative is an instantaneous rate of change. It is the slope of the tangent, the rate of change at a moment. When speaking of the rate of change, there are two rates of change that can be associated with a function. Average rate of change and instantaneous rate of change. Instantaneous rate of change is the derivative. Average rate of change is the slope of the secant. So think about slope of the tangent versus slope of the secant. Okay, let's go. So average rate of change on an interval. This is if you were doing the change in y over the change in x, or so I could say f of b minus f of a over b minus a for some interval from a to b. This is the slope of the secant line. You could say, yeah, just 2 points. So slope of the secant. If I want the instantaneous rate of change, and this would be at a point, you could say that this is f prime of x for some point, or f prime of c. This could be the slope of the tangent. We could even say the limit is h approaches 0. F of x plus h. Taking it way back to limit. F of x plus h minus f of x over h. So this would be the average rate of change. This makes it the instantaneous rate of change. So if I wanted to, I could put up here f of x plus h minus f of x. With no limit in front, this is the slope of the secant. As soon as we've got this, this is the slope of the tangent. You could also say the limit of x approaches a. This is f of x minus f of a over x minus a. X and a are getting closer together. This is the slope of the tangent. If I go over here and I just said f of x minus f of a, x minus a. Slope of the secant is an average rate of change. Super important. Slope of the tangent is the instantaneous rate of change. A tangent line touches a graph at one location. It's an instantaneous rate of change when I find its slope. If I want to find the average rate of change on this interval from 2 to 12, what I would do is I would say f of 12 minus f of 2 over 12 minus 2. So the same way you would have a long, long time ago, f of 12 is 8. I'm going to move this down a second. F of 2 is 5. 12 minus 2 is 10. 8 minus 5 is 3/10. So I have an average rate of change of 3/10. If I go up to my graph, here I plotted a bunch of points. I'm actually going to connect them. I know this should be a nice smooth curve because I know this function is differentiable. I've got these points on here. That was a pretty good curve. I don't know if anyone else stopped the video and were like, whoa, that was a good curve. And then, that's not a good way I said it, and then called somebody over and were like, hey, check out this curve. But if you need to stop now to call anyone over just to show someone how good that is, just saying, you can. Oh no, pride cometh before the fall. The next line that I do is going to be like this. So if this is 3/10, 2 to 12 would be from here to here. And if I were to find, that really wasn't that good, the slope of this line, I would go up 1, 2, 3, right 10, and I would have a slope. So average rate of change. If I want the instantaneous rate of change at x equals 4 and x equals 6, and right now I can't find them exactly because I don't have a function, but I just want to know, is the instantaneous rate of change at x equals 4 greater than the rate of change at x equals 6. So add a moment. So f prime of 4 and f prime of 6. That's what we're comparing. If I go up here to the graph and I say, well, at 4, I can draw a line like that for my tangent. At 6, it's going to be more like that. It looks like this first one is steeper, which means that f prime of 4 is greater. If I justify this, the slope of the tangent is greater at x equals 4 than the slope I'm trying to get better about not putting my head in front of things or moving stuff around. I swear I'm trying. The slope of the tangent is greater at x equals 4 than the slope of the tangent. X equals 6. At x equals 4, the tangent line is steeper. Ta-da! We did it! One page down already. Oh man, this is so exciting. Okay, so what did you learn? Average rate of change versus instantaneous rate of change. Go over those in your head. Average rate of change. What's the difference? What's the similarities? Average rate of change, slope of the secant. Instantaneous rate of change, slope of the tangent. Slope at a moment. This is slope over an interval. Okay. So we're going to go and we're learning another theorem. It's called Rolle's theorem. Let f be continuous on the closed interval a to b, so make sure you put brackets around that, and differentiable on the open interval a to b. If f of a equals f of b, and then here's where I'm going to pick this up. So if all of these conditions are true, if a function is continuous on the closed interval, differentiable on the open interval, meaning you can take the derivative, and if f of a equals f of b, meaning the starting point and the ending point are exactly the same thing. The y value in the beginning, the y value at the end of the interval are exactly the same thing. Then there is at least one point in the interval from a to b, so in the open interval, so somewhere within there, where f prime of c is equal to 0. Okay, so let's go back to that first graph and see if this makes sense. Let's pick some place, an interval, where I start and end and have the same values. What about here and here? From 1 to 16. See how the average rate of change here? What is f prime, what is the average rate of change between x equals 0 and x equals 16? 0. I didn't suddenly get glasses or a monocle or something. That was just me saying 0, like making it with my hand and doing it. It's good for you to know. Okay, so I've got a slope of 0 here, but what this theorem is saying is if f of a is equal to f of b, this function is continuous and differentiable, which we know it is. There's going to be some place between 0 and 16 where f prime of c is equal to 0. Look up here. See this maximum? Hey, it works. Rolle's theorem applies. So let's look back here. Okay, consider the function on the presented on the previous page. So we just did it for 1. Does Rolle's theorem apply? So I just said that it did from 1 to 16. What about from 2 to 14? So I'm going to say right away f of x is differentiable because we know that for sure. It was given to us. And I'm going to be even more specific. I'm going to say on 2 to 14, therefore continuous on 2 to 14. Okay, so I've got that part. The next part says if f of a equals f of b. What is f of 2 and what is f of 14, and are they equal? F of 2 was 5. F of 14 was 5. Hooray! Therefore, rules applies. Or rules can be applied. I didn't just suddenly make this plural, by the way, and then put it in parentheses. This would be like Rolle's theorem, so possessive of the theorem. Rules can be applied. So we'll say yes, we can. And what that means is between 2 and 14, x is 2, x is 14, somewhere in this interval, there's going to be a place where the derivative, the slope of the tangent, is equal to 0, which is going to be at the same place we talked about before. Okay, let's do another one. What about 2 to 8? Well, I already know f of x is differentiable on this interval from 2 to 14. Oops, sorry, closed interval. Therefore continuous. So this is a good start. Good, good, good. But I want to check, is f of 2 equal to f of 8? Well, f of 2 was 5. F of 8 was 11. What? So we've got 5 and 11. 5 doesn't equal 11. But f of 2 does not equal f of 8 because 5 doesn't equal 11. Therefore, rules cannot be applied. It's amazing how writing something in caps suddenly makes it look like I'm angry. I'm not angry. You can see my face. Does this look like a face of somebody who's angry? Okay, I hope not, because I'm actually not angry. I'm just saying, no, it can't be applied because the endpoints are not equal. Okay, determine whether Rolle's theorem can be applied. If it can be, then we can use it. Yeah! I'm going to start on the one on the right. Can Rolle's theorem be applied here? So let's check. Is this function differentiable and continuous? It looks to me like it's going to be easiest to check for continuity first, because this denominator can't be 0. You can't divide by 0. That means x cannot be -2. Oh man, it's in the interval. I did this one first because I just needed to like rip the band-aid off. Actually, never rip a band-aid off. Who does that? Don't do that. Take it off nicely. Use water if you need to, but don't rip it off. Anyway, Rolle's theorem cannot be applied as g of, I can say as g of x is not continuous, and you have to say on this interval. So it's not continuous on the interval from -4 to -1. If a function is not continuous, you can stop there. You don't have to do anything else, just rules can't be applied. And then I saved this one for last because Rolle's theorem can be applied here. Oh wait, I just gave it away. It's like giving away the ending to a good book. Okay, so this one I'm going to say, is this function continuous? Yes, it's a polynomial, so it's going to be nice and smooth. So I'm going to say g of x is differentiable on -3 to 0 and continuous on -3 to 0. The next thing that I want to do is figure out, okay, can I set, or I'm sorry, the next thing I want to know, I almost did the derivative because I'm so used to doing that. What I want to do is I want to see, is FA equal to FB? I already kind of gave it away before, but we're going to do this anyway. This would be 9 times -3 squared would be 9 minus -3 to the 4th power. Over here it'd have 0 minus 0, because I'm putting in 9 times 0 squared minus 0 to the 4th. So you just get 0. This would be 81 minus 81. Yeah! Therefore, rules can be applied. And then I know this is the moment you've been waiting for. You're like, okay, we did this thing, but will we get to use it? And this is the only time that we're doing it so far. But on this one, if you want to find the value of c, let's think about what Rolle's theorem said. Said if a function is differentiable on a closed interval and a to b, and continuous on the, let me start over. If a function is continuous on a closed interval from a to b and differentiable on the open interval from a to b, and f of a is equal to f of b. Then what can happen is that there's somewhere in that interval where f prime of c is equal to 0. So what I need to do is find f prime of c, or in this case, g prime of x would be 18x minus 4x to the third. And I want somewhere where this derivative is equal to 0, and it has to be within this interval from -3 to 0. That's what I'm trying to find. So when I factor anything that I can, I'm going to take out an x and a 2. I'd be left with 9 minus 2x squared. And then I want to say, okay, this would be 2x is equal to 0, x is equal to 0. We're like, that's not in that open interval from -3 to 0. So that can't be my value of c. So what if I try over here? 9 is equal to 2x squared. I added 2x squared on both sides. 9 over 2 is equal to x squared. I take the square root of both sides. I'm introducing the square root, so this can either be positive or negative. Because I'm looking from -3 to 0, you could also say this would be negative, and then take this square root of 9 and make it 3 over square root of 2. 3 over square root of 2. That's the same thing. But it's up to you how you do this one. So if you want to do this, so this would be my value of c. C equals -3 over root 2. And no, you do not need to rationalize this denominator. You're in calculus now, which means you don't have to spend your time doing such things. No, I'm just kidding. It just sometimes makes these answers look more complicated, so there's no reason to do it. But we found our value of c guaranteed by rules. This makes the derivative, g prime, equal to 0, and it's within that interval. Whoop whoop! You did it. Okay, thanks for being you. Thanks for working. I really appreciate it. Bye!